So because of these limitation, we cannot implement Carnot's reverse cycle for the vapor compression cycle. So what's the solution for that? The solution is ideal vapor compression cycle. Now in case of ideal vapor compression cycle, what's the change in the component? The only component, the turbine, is replaced with the expansion valve. By using turbine, although we can get certain work output because of the expansion, but the cost of the turbine is much higher compared to the expansion valve. So the practically, expansion valve is more convenient, more feasible than the expansion turbine. Now let's see now the TS diagram, how the TS diagram is modified for the ideal vapor compression cycle. Now 4-to-1 process is the evaporator in which the heat is absorbed. Now you can see 4-to-1 is the absorption of the heat, the cooling effect which is produced in the evaporator. So the QL is absorbed in the evaporator. So after evaporator it is compressed. So isentropic expansion from 1 to 2. And then in the condenser, there is no more constant temperature heat rejection process. In case of the Carnot cycle, that heat rejection process was isothermal, but here from 2 to 3 the temperature is changing up to this point, and then this is a phase change process, constant temperature. So this is basically the combination of the sensible cooling as well as phase change cooling. So that means the temperature within the condenser from 2 to 3 is no more constant now. And now the process 3 to 4. Previously here was a turbine. So the turbine was isentropic expansion, but now we have expansion device, just like a throttling device. So that during the throttling process, the enthalpy remains constant. So this is basically isenthalpic process. So this is no more, previously it was a straight line, constant isentropic process. So but now it is isenthalpic process. H3 is equal to H4. So this process keep on continuing, right? So these are the 4 processes for ideal vapor compression cycle. Now if we want to see the performance of this ideal vapor compression cycle, now let's see. The first was the expansion valve. So in case of expansion valve, H3 is equal to H4. So H3 is equal to H4. Whereas in evaporator, the heat is absorbed. QL is absorbed in the evaporator. So that QL is basically the difference of the enthalpy. So H1 minus H4. That heat absorbed QL is basically equal to H1 minus H4. This is kilojoule per kg. So if you want the total heat absorbed, you have to multiply with the mass flow rate of the refrigerant. This should be mass flow rate of the refrigerant times H1 minus H, but this is the specific heat absorbed. Now come to the work input to the compressor. Again, W in is equal to the difference of the enthalpy. H2 minus H1. I'm using the energy balance. I'm applying the energy balance for each component. If you recall, the energy balance is Q minus W is equal to change in energy of the system. So in case of compressor, there is no heat in or out from the system, the only is the W. So that W is equal to the H4 minus H2 minus H1, because this is an open system. So that's why the Q minus W will be equal to the difference of the enthalpy. If this is a closed system, that Q minus W would be equal to the change of internal energy of the system. So the compressor work input is equal to H1 minus H4. And lastly, the condenser. In condenser, the heat is rejected to the atmosphere. So that Q rejected is equal to H2 minus H3. So that heat rejected in the condenser is equal to H3 minus H2. Now how to evaluate the performance of the ideal vapor compression system? Now the COP of the ideal vapor compression system is equal to the cooling effect produced or the heat absorbed in the evaporator divided by the work input. So the heat absorbed is equal to H1 minus H4, and the work input in the compressor is equal to H2 minus H1. Basically that should be equal to H2 minus H1. Please make that correction. This should be H2 minus H1 because the enthalpy at 2 is greater than enthalpy at 1. So this should be H2 minus H1. So that will give you the enthalpy of the coefficient of performance of ideal vapor compression system. Now, actual vapor compression refrigeration system is slightly different than the ideal vapor compression system. This is because of the fact that the irreversibilities exist in the actual system. Now these irreversibility are the results of the fluid friction, because once the refrigerant flow into the inside of the tube, then there is a fluid friction between the outer wall of the tube and the refrigerant. So because of that, there is a pressure drop. This is one of the reason of the irreversibility. And the second reason is the heat transfer to or from the surrounding, because we cannot assume it as ideal adiabatic process. There is always, in actual process, there are always heat drop either from surrounding to the system or from system to the surrounding. So that's why the COP decreases as a result of these irreversibility. So in case of a TS diagram, if we look carefully, that let's say in case of compressor 1 to 2, previously we assume isentropic compression, but actually it is not. It is not isentropic. There is actual compression. Similarly, in case of the condenser, now there is a slight pressure drop. You can see in actual process there is a pressure drop, and we assume that in ideal vapor compression, we assume that the 0.4 is a saturated liquid, but in actual case, the outlet of the condenser is a subcooled liquid. And similarly, in the expansion valve, after the expansion take place, there is a pressure drop in the evaporator. You can see that there is a pressure drop in the evaporator. So because of this irreversibility, the coefficient of performance of the actual vapor compression refrigeration cycle is slightly lower than the ideal one. In ideal case, we also assume that the inlet to the compressor exists at this point, the saturated vapor, but in actual, inlet to the compressor is a superheated region. Now let's try to solve one numerical problem which is based on the knowledge that we have gained up till now. Now consider a storage plant is required to store 20 tons of fish. The temperature of the fish when supplied is 25 degrees C. So assume that from the Tarbela lake, someone supplied the fish at 25 degrees C, and you want to store that fish, and the storage temperature is minus 8 degrees C, whereas the freezing point of the fish is minus 3 degrees C. That means you want to freeze at minus 8 degrees C. However, the freezing point of the fish is minus 3 degrees centigrade, and the specific heat, as you know, changes with the temperature. So the specific heat above the freezing point is 2.93 kilojoule per kg per degree C, whereas the specific heat of the fish below the freezing point is 1.25 kilojoule per kg per degree C, whereas the latent heat of the fish is 232 kilojoule per kg. Now you want to achieve the cooling, that required cooling, from 25 degrees C to minus 8 degrees centigrade within 8 hours. So what should be the capacity of the refrigerating plant? So basically this is a design problem that you want to store certain item. This is particularly example of the fish. It can be a fruit, anything else. So how can you calculate the capacity of the refrigeration plant? Because you want to install that plant, so you must know how to calculate how much capacity of the plant is required. So accordingly you will purchase that plant, or accordingly you will build that plant. So let's try to solve this problem. So basically in this problem, you need to calculate the fish storage plant, and the fish is supplied at 25 degrees centigrade, and you need to store at minus 8 degrees centigrade. So that's the freezing required. However, the freezing point of the fish is minus 3 degrees centigrade. So basically you have to calculate how much heat you have to remove from 25 degrees C fish to minus 8 degrees centigrade. So if you can calculate the heat removed, heat extraction, that will be the capacity of your plant. So basically from 25 degree centigrade to minus 3 degree centigrade, that's a sensible heat because that's a temperature difference, the heat as a result of the temperature difference, and you can calculate that heat as mcp delta t. Once the 20 ton of the fish reaches at minus 3 degree centigrade, then inside the fish there is water, blood, so that means then there is a phase change process. So minus 3 degree centigrade, so 25 degree centigrade to minus 3 degree centigrade is sensible cooling. Then minus 3 degree centigrade to minus 3 degree centigrade, that means that's a latent heat. So the whole of the fish, 20 ton of the fish, has to convert from minus 3 liquid form to minus 3 solid form. And then minus 3 degree centigrade to minus 8 degree centigrade, again temperature difference, the sensible cooling. So that means basically you have to remove three types of the heat. One is the sensible heat, 25 degree centigrade to minus 3 degree centigrade, and then minus 3 degree centigrade to minus 3 degree centigrade, which is latent heat, and then minus 3 degree centigrade to minus 8 degree centigrade. So let's calculate. So first, that means you are given the Cp value above the freezing, below the freezing, and then the latent heat, and you are required to achieve this cooling within 8 hours, and the mass of the fish is 20 ton. That means 20 multiplied by 1000. So you need to calculate the capacity of the plant. So first of all, let's try to calculate the heat removed from the fish above the freezing point. That means from 25 degree centigrade to minus 3 degree centigrade. That's the sensible heat, which is calculated as mcp delta t, but here cp will be above the freezing point. So this heat is 1.64 into 10 to the power 6 kilojoule. And then the second heat, Q2, is the latent heat, minus 3 degree centigrade to minus 3 degree centigrade. So here, this is a sensible heat from minus 3 to minus 8. So this is minus 3 to minus 8 degree centigrade. But now we'll use the Cp value below the freezing point. And the third heat is the latent heat that I discussed with you, that minus 3 degree centigrade to minus 3 degree centigrade. So that's the latent heat. So that's the value. So the total heat removed is Q1, Q2, Q3. So that's the total heat which is we have to remove from the fish in order to achieve the cooling. Now the question is, we have to achieve that cooling within 8 hours. So that means within 8 hours mean we have to divide with the 8 first. Then in order to convert into minutes, we have to divide with the 60. Then in order to convert into seconds, we have to divide with the, so in order to convert into hours, we have to divide 8 into minutes and then into seconds, right? So if we simplify, that will be 222.39 kilojoule per second. So that's the heat that we have to remove, right? But we know that 1 ton of refrigeration is almost equal to 3.5 kilojoule per second. So if we divide that kilojoule per second, that will be 63.54 tons of refrigeration. So that would be the capacity of the plant required. Normally in our room we install 1 ton of air conditioner. So you can think of that almost 63 air conditioner. I mean, just to give you some idea, right? So that's the end of the lecture number 3. Again, if you have any questions, you can email me, you can come to the interaction session, right? See you in the next class next week. Assalamu alaikum.